Now we'll use this in weighing my dog. I have a Shih Tzu named Reign of Terror. She's a little mischievous, and when we go to the veterinarian, Reign squirms on the scale. So every time we weigh her, we get a different weight. This last time we got 13.9 pounds, 17.5 pounds, and 14.1 pounds. What we want to know is how much Reign weighs. And this will be the basis for a decision. This is important. If her weight has gone up, her food intake will have to go down. And for her, this is a matter of life and death. So we don't want to make the wrong assumption and draw the wrong conclusion. So if you've ever taken a statistics class before, you know you can take these measurements, add them up, get the average, 15.2 pounds. You can calculate the standard deviation of these three measurements and also the standard error and come up with a 1.16 pound standard error, which when you show it graphically, this red curve now shows the belief that results from those three measurements, the distribution. The peak of that hill is at 15.2 pounds, and one standard deviation on that curve is our standard error of 1.2 pounds. So you can see looking at this that yes, it's most likely that she's 15.2 pounds, but there's a lot of that curve that sits outside of the range of 14 to 16. So yeah, she's probably between 14 and 16 pounds, most likely between 13 and 17 pounds, but she might even be lower than 12 and higher than 18. That is a really wide range, and it's not a great basis for making a decision. Now you can see the three measurements there, those three white vertical lines, and you can see why our belief is so dispersed, because those three measurements are pretty dispersed. It's hard to capture all that in one distribution. So let's try it again with Bayes' theorem. So the way we'll do this is, instead of A and B, we'll substitute in W for her actual weight and M for the measurements that we took. Now this term over here, the probability distribution of the actual weight, is our prior. This is what we believe about her weight before we put her on the scale. The probability given a weight of getting certain measurements are the likelihood associated with those measurements. And then the posterior is what we believe about her weight given those measurements. So you can think of this as we start with a belief, we take some measurements and we update it, and then we have a new belief when we're done. This term on the bottom we're going to ignore for the most part. It'll be a constant, but it's called the marginal likelihood. So we're going to start by not assuming anything about her weight. Could be 1 pound, 10 pounds, 20 pounds, 100 pounds. We're going to let this be uniform and we're going to let the data speak. So now our formula looks like this. We can further simplify it. And so we want to calculate this. We want to calculate the probability of our measurements occurring given a weight. And we want to do this for all of the possible weights. And then we'll end up with a new distribution, which is our belief. What's the probability of each of those weights occurring given the measurements? So these two things are identical. So let's start, for instance, by assuming, what if she weighed 17 pounds in reality? Now, because our measurement process is very noisy, as we saw, if she weighed 17 pounds, we would expect those measurements to be distributed as shown here. Some would be up way above 18 pounds, some would be down around 14 pounds, where we actually measured, but not very many of them would be. So to calculate now the probability of our measurements occurring, given this weight, we find what the probability of each individual weight is of occurring, and we multiply that times that times that. Now these two are pretty small. When you multiply two small things together, they make something very small. So the probability of her being at 17 pounds is pretty small. We shift our belief over and say, well, what if she was 16 and a half pounds? What if she was 16 pounds? And we recalculate it each time, multiplying all of those actual probabilities together. And then by the time we're done, this is what we've measured at each of those weights. This is the likelihood of each of those occurring. And you can see that the maximum likelihood occurs at 15.2 pounds. And this is commonly called the maximum likelihood estimate, where you start with uniform assumptions on your weight. And it just so happens that the standard error on this is exactly what we calculated before. A very cool connection here. When you take the average and calculate standard deviation and standard error, it gives you the likelihood that you would get by doing Bayes' method and assuming a uniform prior, not assuming anything about what the result's going to be. So, we've already established, though, that that's a really broad result and not helpful. So we need to start over now, and let's start with what we know. So some background information. Rain was 14.2 pounds the last time we went into the vet. And she doesn't seem noticeably more heavy to me. My arm is not that well calibrated, but I'm going to assume that she's within about a pound of where she was before. So I take that prior, and this is the form that it takes. A normal distribution centered on 14.2 pounds, and you can see that most of that bulk is within plus or minus a pound. And it extends a little bit further out. I allow for the possibility that she's actually gained a lot or lost a lot of weight, but probably she's pretty close. This is what I believe before I even put her on the scale. This is the probability, the probability of her being a given weight. So this time we're not neglecting the prior term. We're not setting it constant. We're going to use it. And the way this plays out now is we assume, okay, what if she were 17 pounds? Well, we need to multiply that now by the probability of our prior showing that she's 17 pounds, which actually makes that quite small. Now we calculate and multiply the three probabilities of our measurements occurring. So now we have something small times something very small times something very small. So we get a very small result probability that she actually weighs 17 pounds. And now we repeat this process at 16 and a half pounds and 16 pounds and 15 and a half pounds and 15 pounds all the way through. And then by the time we're done, we tally up all of those and we get this new posterior distribution. It's normally distributed at about 14.1 pounds, and it has a standard error of less than a pound. You'll notice it's even narrower than our original prior. So we've taken our original belief and we've been able to sharpen it up just a bit. And so incidentally, the peak of this curve is called the maximum a posteriori result. If we had to choose one value to represent our belief, that's not a bad one to choose. And now we compare this with our original estimate. It's labeled non-Bayesian here, but more accurately it could be Bayesian with a uniform prior. You can see that it is much broader, and also the peak of that curve is in an entirely different place. So the answer that we got, it's more confident because it's more centered, and it's probably, based on what we know, closer to being correct. So this is how Bayes' theorem is used most often in data science or in analysis. It's a prior that you then update based on your measurements to sharpen up and get a revised set of beliefs. So there's a lot of times that it makes sense to use Bayesian inference. Sometimes we just know things. Like if we're measuring age, we know that everyone is more than 0 years old. And so we can take that information and build it in, and we can get sharper estimates with fewer measurements. Now, so it should, if you're paying attention, make you a little bit nervous. We humans are actually not always aware of what we believe, and putting it into a mathematical distribution can be very tricky. More importantly, the reason we're measuring something is because we want to learn about it. We want to be able to be surprised by our data. So if we believe something that's not true, it can make it hard or impossible to learn from our data. I like how Mark Twain phrased this. He says, "It ain't what you don't know that gets you into trouble, it's what you know for sure that just ain't so." So the way to avoid this pitfall is to always believe things that we think are impossible, at least just a little bit. So by leaving this room for something to be possible, we can do like Sherlock Holmes says, and once you've excluded the impossible, then whatever remains, however improbable, must be the truth. We don't want to exclude the improbable out of hand, because then we're left with nothing. Alice, in a conversation with the Red Queen, summed it up well too. "There's no use in trying," she said. "One can't believe impossible things." "I dare say you haven't had much practice," said the Queen. "When I was younger, I always did it for half an hour a day. Why, sometimes I've believed as many as 6 impossible things before breakfast." So the secret to using Bayesian inference well is to keep believing impossible things. Thanks for your attention. Here's how you can get in touch with me if you'd like to carry on the conversation. I look forward to talking with you again soon.